Hey, look, it's what this class is doing. Really?
Right. Hello, everyone. Welcome. Any questions before we begin? Still grading your exams. I should have that done by Thursday, hopefully. I've graded some, but not all of them. So the plan today is I'm going to go over the practical. We're going to go over the secret thing that should take not so long. And then, if you remember, at the beginning of the semester, yes, sir. Yeah, good. Oh, okay. Oh, um,
Get out.
what do you guys think? Should we give him a second chance? I'm
Send him to the break.
I'm just kidding. So the practical is no. The practical is I call it a exam, but it's just a lab, right? So I will give a bonus lab. I always do this. It's called the Big Num crypto. So that's a bonus points lab. So if you miss something, you can just do that. If you've missed a lot of assignments, then obviously it only counts for one missed assignment. Does that make sense? So you can do that instead. Any questions? You guys still need to demo the Pi Crypto Dome though, if you haven't done so already. But you can do that one instead. Got it? Yeah. Any questions or anything? Anything else? All right, great. So we're let's, as I said, so my plan today is to go over the scavenger hunt, right? And work out the solution. And then after that, if you remember at the beginning of the semester, I said I cannot explain SSL right now, right? I cannot tell you what SSL is and give you a meaningful explanation. We have to go through all these steps, all these things, and then at the end of the semester, we get to it. So that's where we are today. So I'll be able to now go over SSL and you'll understand everything about it. And in fact, SSL, you can think of it as a protocol, actually, it's got a networking component to it. And it's also, there's SSL 1, 2, 3, and that has been actually replaced by something else called TLS. And currently which is also a protocol, and it provides the network encapsulation things and things like that. But it's really, although it provides all the networking things, what is it doing in the background, right? The exchange, and then once a key is exchanged, what's the cryptography, some kind of an AES, right? And so as we get to TLS 1.3, which came out in 2018, so about, what is it, 8 years ago? No, 6 years ago, right? 2018 is 6 years, right? About 6 years. We're going to talk about all the issues, right? So we've talked about RSA, for instance, and how there was a padding problem, if you remember. That's why we had to use PKCS, if you remember, right? And there's been many attacks beyond factorization on these protocols, right? And I've said, for instance, that for key exchange, we have at least 3 methods. Do you guys remember what these 3 methods are for key exchange? RSA is one. What's another one? Diffie-Hellman. And the third one?
AES.
Elliptic curves. Yeah, AES is for confidentiality. So elliptic curves, which is kind of the last one, right? So I'll cover elliptic curves, but what's fun about elliptic curves is actually it ties into Diffie-Hellman. And you already understand Diffie-Hellman, right? So I'm just going to add that component, and we're going to talk a little bit about it. And we're going to talk about why that's important. Does that make sense? And it has to do with something called forward secrecy. Okay, and I've alluded to this before. We talked about 2 of the main problems of cryptography today. One of them being what? Quantum computers, right? So are the algorithms quantum ready? The other one is the problem that hackers, rogue governments, whatever it is, people are collecting a lot of your encrypted data, and they have it. They have it in some vault, and it's stored there. And what are they waiting for? They're waiting for either a quantum computer, or they just want to steal a private key. What if they hack your computer and they get your private key, then they can start decrypting your material, right? So that's called forward secrecy. And so, there's techniques to address that. So we'll talk a little bit about it, but it all ties in nicely to this idea of SSL and actually the current version, TLS 1.3. Does that make sense? And these things are changing all the time, by the way. So, today something is, in favor, then they find they break it somehow, and so they need to implement something else. Okay, so that's the plan today. And then the lab this week should be a nice lab. The topic is certificate authority, right? But it's the same thing. It's the whole SSL or TLS process in a very simplified way. The key thing being that you will become a certificate authority, and you should understand how the process works of a client, like a web browser, communicating with a server, right? And the whole process. So that's basically the discussion this week. All right, but before I get into that lecture and everything and go over the algorithm, I do want to go over the solution, to make sure everyone understood it, and you guys can help me out, right? So I'm going to go ahead and start the virtual machine here. Okay. And I guess while it's doing that, we can read the problem, right? So the case, the scavenger hunt. That should be here. So you were supposed to open this, right? Download all the files into your folders. Then you were going to read the document, the Word document, and then the hint basically is to create a few folders, right? And drop all the corresponding files into each of these folders and then break things. So I'm going to open up the Word doc. Okay. And let me know. So I should be able to log into it. Here we are. All right, so I'm going to open up the terminal. All right, so /l std. I should have all the files already. Let me go into Scavenger Hunt. CD4 quiz. And you can see I already put everything into the folder. So let's read through the Word document. So basically, you have to find several pieces of information to arrive at the final piece of information that would reveal the secret, right? So, the idea was I named things so that you knew what folders to create. So break into the CIA vault and retrieve a secret of great importance. To break into the CIA vault, you need to find a secret code. This code is made up of 3 other codes that must be concatenated together. The 3 codes are stored in the vaults of JP Morgan Bank in Washington, Mackinac Island First Bank, and the Kremlin. You will first need to break into these institutions and retrieve the respective codes. Once you find the secret of great importance, let us know. Also, read the intercepted top secret communication. If you remember, we did a quiz just on this. right? We had done a quiz just on that. This message will self-destruct, so be careful. All right, so that was basically the problem, right? So you would download all these files, and then you create these folders: CIA, JP Morgan, Kremlin, and Mackinac. If you notice, I even provided the Python code, so you really didn't even have to get code from the GitHubs. You could just move the code and everything was labeled. All right. I provided these agent, private, and public. So you're an agent, right? So you were the agent breaking into the thing. So these were your keys, right? And so that was the idea. So where do you start, right? So where do you guys want to start? Or how did you guys start? Which one of these did you go first, sir? JP Morgan. All right. So CD, JP Morgan. Okay. Clear. Oops. All right, so JP Morgan has 2 volt. It has an AES volt JP Morgan encrypted, and it has a cipher AES key JP Morgan, right? So that tells you something. This is actually one of the things we did in the demo, right? Okay, so all you needed was the key here. So let me open up this folder. Since you were opening a key, right? What do you need to use? You would use your own private key, most likely. I didn't label it because I wanted you guys to figure it out. So these are the keys. So I'm just going to copy agent private into JP. Okay, here we are. So it should be this one. So now we do clear ls-l. All right. So I have agent private.pem in there, right? So we know from the process, we have AES hack JP Morgan, and then we have RSA hack JP Morgan. So we use RSA usually to exchange the key, right? It's one of the protocols that we know, so we can go into RSA. Okay, so you can see here, basically it says cipher AES key. This is the encrypted symmetric key for AES. See here, I just wrote key, but all you needed to do was say agent underscore private, right? .pem. All right, and read bytes. And then you create the object, you load the key, and then cipher RSA decrypt encoded data, which is the key that you read, and you're going to actually write it into the decrypted file, pretty much like you did in the PyCryptoDome. Okay, so we can proceed to run this one. Okay, that should be done. So you take a look at it and you can see that it did generate a new file now. A decrypted AES key JP Morgan. That should tell you a lot, right? So decrypted AES key JP Morgan. So now we go to the other Python script, which is AES hack. Oops, sorry. Nope. All right, so we go in here, and that is AES Vault JP Morgan. So Vault is basically the thing that has whatever secret you're looking for. We use the decrypted AES key from JP Morgan. Pretty much this code should work. There's nothing you had to do there. So and it should print out the message, right? So Control X. Oops. So I did nothing. So now I'm just going to run it, Python 3. And there you go. That's one of the secrets, right? So that's one of the secrets. JP Morgan, which was 111011. You see that? So that was basically the process. All right. So now we found that secret. So we can go ahead and go back to what else did you guys do then to that? The Kremlin, right? So the Kremlin seems to be, something that we did in a quiz. CD Kremlin. Clear. Start now. All right. So the one with the Kremlin had this top secret communication, right? And we had talked about this, right? That people sometimes implement, incorrect ciphers. So there is, for instance, a trick where if you've intercepted one cipher and another cipher, and the same key has been used on both, you can start to try to break it. But this one was very simple. It's just a concept you guys already know. What was the solution to this one? So it says, top secret, the Russians have implemented an insecure cipher. We can derive the key from intercepted ciphers and messages. We know the block and key are size 16 bits, and we intercepted the plain message in binary and the cipher in binary. So that's a plain and a cipher. Can we derive the key? We can, right? And how do we do that? Just with XOR, right? So you perform so you have to do this manually, literally. You have to XOR it. So, yeah. No? Yeah, so it's going to be, what is it? So 0, 1 is 1, 1, 1, 1, right? And then the next one is going to be 1, 1, 1, 1, right? Okay. And then the third one will be 1, 0, 1, 0, right? Okay. And the last one is going to be 0, 0, 1, 1. Correct? All right. So that's what you had to do. So you do, the XOR operation that we've been doing all semester, and you've broken the key, right? So that's the key. So now you go ahead and it says, well, there's a vault. So, and if that's a bin file, so that's the encrypted file. So then you can go to the code. So nano code. All right. And basically here you can see there's a secret key that's missing, right? So basically this is what the hint was to read the top secret message. So then you could do 1, 1, 1, 1, right? Then 1, 1, 1, 1, then 1, 0, 1, 0, 0, 0, 1, 1, like that. And then you do this. So now let's run it. And there we go. 5454 was the other code. Okay, the second secret code. Just like that, right? I think I saw a movie where they did this, like got one code and then the other code. And then I was like, I'll do that in a quiz. So anyway, so they did that. And then that just had the third one, which we had practiced that one quite a bit, right? You guys know how to do the RSA factorization with FactorDB. So we go to, all right, so now we would go to Mackinac, right? So let's go in there. Okay. Right. All right, so here we have Mackinac Bank public key, okay? Mackinac Bank vault, okay? So I even made it very easy, right? I didn't even give you like the certificate where you have to go extract it or anything. I just kind of just gave you the thing that would plug into the code, basically. So if you look at the code here, this was the familiar RSA code that I mentioned that we would use for factorization. Notice that this is the cipher, right? I wrote the code here and it's blank. You needed to replace this with what was in the file. And then, of course, you needed here the code calculates P and Q as primes, but you obviously needed to get those, right? So you needed to factorize something. And you guys hopefully understand. All right, so how to do that. So we go to cat. We can cat Mackinac. Okay. And this is the code. So you can just copy this one. So this was like a cipher. Copy this. Right. So then you can go over here. right there, right? So we can comment out this. And then the cipher will paste. So that's the cipher basically that you needed to have. And now all that's left is to factorize something. So what do you know? You have something that says the public key. So you can look at it back and there it is. See, it says public equal E and N, and then public equal E and a number. And we've learned that we can take N, factorize it, and that could give us the P and Q, which are then the two prime numbers that would allow us to break RSA, right? That many people have tried to break over the years. So we can grab this number. Then we need to go to factordb.com, or if you have a quantum computer or a simulated. Okay. So factordb.com. All right, so here is the text box. So you can paste that in there, right? And factorize. And there you go. Those are your two prime numbers, right? So you can write them down. So it's going to be 18669 65 669 65 369, right? That's one. And then the other prime number is 362 85 18337. Okay, so those are the two prime numbers. And now you can then go back to the code example. And all you needed to do was replace P and Q with these numbers, basically. Okay, so I'm going to go down here, like right here, right? So you can, like that. So I'm going to add P, and that's 18669 65 369, and then Q is gonna be 362 85 18337. All right, those are your two prime numbers. So now you can proceed to decrypt. I'm just going to go ahead and run this one. On 3. And there you go. That's the third code, which is 777123. 777123. And that's it. Now you have the three codes. You know, by breaking two of them, you actually hacked the thing, right? You broke RSA or you broke the Russian bad encryption. And then, and the other one was something that was sent to you. Basically, that's the, in essence, right? Because you had the private key. You didn't really have to do any breaking. So someone had broken it for you and they just securely sent that information. So now the last part of this, you can clear, right? And now we go to the CIA vault. Okay. Oh, all right. So now obviously the secret message is here. This is the text that the quote from a movie, right? And you needed to go into the code. So hack. All right. So you can see here are the three secrets. I don't remember the order, honestly. So if you guys remember the order, tell me, like which one, what was the first?
JP Morgan.
JP Morgan.
Last one, I think.
Okay. So JP Morgan was 111. All right. So 111 0.1. And then you said the last one was Mackinac. Okay. So that would be the sevens. 7, 7, 7, 1, 2, 3. Okay, great. This is so 7, 7, 7. I didn't do this, but this, you can try, right? Trial and error. You should be able to figure it out. And then the last one then should be 54, 50. That's it. So once you have these three, they're going to be concatenated. As you can see, there's strings. So now let's go ahead and run it. And this should give you the secret. No, that's not the order, actually.
Yeah.
Yeah, okay. So 5, 4 is first. Five, four, then.
Yeah, split this one.
Yeah, this third one is 1, 1.
Okay, so this one is all sevens. 7, 7. Okay.
No.
Wait.
No?
No, the third one is 1, 1, 1, 0, 1.
The third one is one.
The middle one is complete.
Okay. 1, 1, 1, 0, 1, 1. Like that?
Yeah.
Great. So let's proceed. There we go. That was the secret. The secret charm to create a Patronus, a defensive guardian, is Expecto Patronum. What movie is this from? Yeah, it's one of the Harry Potter movies. I don't know which one it is, but I looked it up. So that was it, right? So, kind of, I always try to use either a potion or some kind of a secret gadget formula or something. All right. Yeah, so that's basically it. It's meant to be fun. And, it covers a lot of the techniques. And this was the scavenger hunt. Any questions, guys? All right, great. So, like I said, if you missed this, you do have the bonus lab. It's not an easy lab, right? It's in C. So but because it's meant to be, it's called a big number crypto. So it uses large numbers. It uses libraries for really large numbers. But it's the same thing. It's like key exchange. Once you've done the key exchange with something like RSA, then AES and things like that. So it's the same concepts, just in C and with big numbers. All right. All right. So that's the scavenger hunt that I wanted to cover. Okay. So I'm going to exit out of here. So I create this